We are the Air Quality Monitoring with UAVs group, sponsored by APIS Incorporated.
So here's our project scope. We've got our level 1 primary requirements and our secondary requirements.
The specifications, it had to run for the same amount of time that the drone could fly, and it had to be within the size of the mounting plate that is on the top, and it had to be less than 2.5 pounds.
So here's how we did our alternatives. We used this table here on the left to weigh our alternatives, and the weights that we came out with are on the right. And you can see that we decided to go with the ozone and the PM2.5 sensor, the onboard memory card, the multi-rotor UAV, smaller, lighter battery than the drone, and the single housing. Alright, for our selection criteria, in the FMEA we identified all the possible failure modes, and we determined the most effective course of action to minimize the likelihood and impact of each. For analysis, we ran some analyses on turbulent flow. The sensors will be used in environments that closely mimic ideal atmospheric conditions. Drone sensors mounted will only be operated in fair weather conditions and with slight moisture, and the anti-vibration payload deck on the drone will be sufficient.
For the analysis, we used SOLIDWORKS to figure out how thick our parts should be so that we could save the most amount of weight possible while still having it be stiff enough so that it won't break when we're landing.
So the airflow analysis, like I said, doesn't matter if it's turbulent or not around these two particular sensors, as long as there is flowing from the inlet to the exhaust. There's a fan there at the exhaust that pulls 1.24 cubic feet per minute, and we determined that was more than sufficient airflow for these sensors to work.
The plan for manufacturing was we have two 3D printed parts. We have one part that is sheet metal, aluminum, and the rest of them are plastic parts that can be cut with just a standard saw and then glued together or taped together.
The electrical design consists of a central Arduino that processes and records data collected from the sensors. All components in the design are off-the-shelf parts that have been determined to be compatible with the power system and central Arduino. The power system consists of a 2000 mAh LiPo battery and boost converter circuit to provide 5 volts to the entire system. It was determined that the entire system will be wired using 26 to 28 gauge wire. This is the wiring diagram of the electrical design. The power system is located in the upper left corner, the sensors in the upper and right hand sides, and other support circuitry in the lower left corner. The design will record location, temperature, humidity, barometric pressure, time, ozone concentration, nitrogen dioxide concentration, and particulate matter of 2.5 micrometers. It was determined that we will sample up to 20 times per second, then averaged to produce a single data point for each second. Data will be stored in a CSV file on a 16 gigabyte micro SD card.
Mechanical design. The aluminum is going to be fairly thin. We figured out that it could be 1/32 sheet instead of a 1/16 sheet, saving approximately 0.1 pounds so that we can get a longer flight time. The ABS printed parts will be printed on a 3D printer that we made sure was big enough, and the ducting for the PM2.5 sensor will be airtight as to not affect the particulate matter. And this is the final design here, where we have the PM2.5 sensor on the top right, and then the big white central housing on the left is for the ozone and the nitrogen sensors and any additional sensors that we needed, like the temperature and the humidity, also the additional sensors that can be added into the system for later expansion.
And here's our Arduino board and our power board. The battery will go on the bottom, slide in right here. And this is the ducting for the PM2.5.